The objective of this video is to derive the sizing law for AC machines. And this video is going to be tying together our sequence of videos that have been developing equivalent surface current density on the inner bore of a stator, along with polyphase windings and a rotating equivalent surface current density, to make calculations for how much torque our machine produces. So in this video, we're going to actually see the principle for how we create torque in a motor, and we're going to relate that to how much torque we can create and some of the intrinsic properties of an AC machine. We're going to be talking about electric loading, magnetic loading, and the average shear stress on the surface of our rotor. Let's start by reviewing the key results of this series of videos on equivalent surface current densities. We've talked about our machine being excited by balanced three-phase currents, and we've written expressions for those currents as follows, where these are cosinusoidal expressions that take an argument, in this case, of alpha W. And in our video on this, we had written alpha W not as alpha W, but we had written it as an expression of omega t plus a phase. And in this discussion, we're just going to consider it as having this argument of alpha W. We're not going to necessarily assume it. It does not have to be in this form right here. It just has to be that IU, IV, and IW are cosinusoidal currents that are phase shifted from each other by 120 degrees and have the same magnitude. And we've talked about going from coils in slots of our stator to creating an equivalent circumferential surface current density on the inner bore of our stator. And we came up with this expression for that equivalent circumferential current density. Now in that video, I was very careful about putting a subscript n on these quantities. It was AC at n of alpha, where the n indicated the harmonic index. In this case, I'm just tracking the harmonic index in the sign expression, and I'm just doing that for convenience because we're only going to be considering the fundamental component. We're only going to be considering the value where n is equal to p, but we're going to prove that. So we're going to keep this as n for now, and then later in the video you're going to see me replace n with p, and I'll point that out to you. And we've noted that when we have a circumferential current density, we can also write this equivalently as a linear current density. So our circumferential current density told us the total number of amps per radian at some value alpha, at some angle alpha, whereas a linear current density tells us the total number of amps per meter at some location on the inner bore of our stator. And from this equivalent winding, we've constructed a current linkage. And we've also noted that we can calculate the fields in our air gap due to the winding, which we'll call the armature field. This is also sometimes called the armature reaction field. So the fields in the air gap that are created by the winding are called the armature fields. And we've got a tangential field, which we can calculate from our linear current density. And we've got a normal field, which we can calculate from our current linkage, dividing our current linkage by our air gap length. So at this point, all of this is a review. This is all a summary of what we've talked about in the preceding lectures. We've talked about how we can take a balanced three-phase set of currents to excite a multi-phase winding and end up getting an equivalent circumferential current density that is located in the inner bore of our stator at the angle that our currents were excited at. And we can convert that circumferential current density to an equivalent linear current density. And we can take these quantities, the circumferential current density and the linear current density, and use them to calculate the current linkage and the fields in the air gap of our machine. Now we're going to introduce one more quantity. We're going to talk about the magnetizing field of the motor. And the magnetizing field is also called the no-load air gap field. It's the normal field in your air gap when your machine is under no-load circumstances. So for a permanent magnet motor, this means that there's no current flowing in the stator. For an induction motor, it means you only have the magnetizing current in your stator. So this is the field that you have in your air gap that is somehow there. Maybe it's created by permanent magnets, or maybe it's created by the squirrel cage on your induction motor rotor, maybe it's the field winding on your salient pole synchronous machine, but it's the field that is created under no load circumstances by some magical means. And as we've written an expression for this right now, we see that this is a cosinusoidal quantity, and in the argument the cosine is the quantity theta, which is the rotor angle. So if this is a permanent magnet rotor, I'm going to sketch this for a two-pole permanent magnet rotor. So for a two-pole permanent magnet rotor, theta is the location of your north pole, or the center of your north pole. And that is also called the direct axis of the machine. If it's a salient pole motor, you can say a similar thing. Theta is now the angle between the x-axis and the location of the center of the pole of our salient pole machine. And this is again called the direct axis. So we've got these expressions for our fields from our winding, and we've got an expression for the field from our magnetizing field. We can now write an expression for the total fields in our air gaps, and then use this with the Maxwell stress tensor to calculate the torque that is acting on our rotor. So in the normal direction of our machine, we've got the magnetizing field plus the normal field from our winding. And in the tangential direction in our air gap, we simply have the field that's created by our winding. We can now use these fields within the Maxwell stress tensor. And so let's review our stress tensor components. And to calculate torque, we're going to be integrating the tangential component of the Maxwell stress tensor on the entire surface of our rotor. And so we can write that out in terms of our field expressions. That is, in terms of the fields that we've got above here. We've got Bn and we've got Btan. And as we've done in a previous video, we can then integrate the stress tensor over the surface of our rotor by evaluating this integral. And we'll do this by plugging in our expression for the shear in our air gap. And if we work on these cosines and sines a bit, let's take this first one here. If we multiply this through, we get the following trigonometric expression. And this is just for this first cosine times sine. And if you recall, P and N are indices. P is the number of poles on P is the number of pole pairs, and N is basically the number of pole pairs of our winding. And for now, we've been keeping it general. But I'm going to show you that in this derivation right now, I'm going to be showing you that P must equal N in order to create any torque. But we know that P and N both have to be greater than 0. They have to be greater than or equal to 1, because you can't have 0 poles, or you can't have -1 pole pairs. And we also know that when we integrate a trigonometric function, when we integrate a sine or a cosine over 2 pi, it's going to be 0. So that means that we need alpha to drop out of this expression. It needs to drop out of our sine or our cosine in order for any of these terms to survive the integration. And so therefore we can immediately see that this first term is going to go to 0. There's no way that P plus N equals 0. Alpha is always going to be in that sine term. Now we're going to do the same thing with this second term over here. And we can make the same conclusion. Well, I mean, for one, the sine of 0 is 0. And again, there's no way that we can pick N so that alpha disappears out of this other sine term. So the only term that survives our integration is this term over here. And the only way that that is going to survive the integration is if we pick P to equal N. So that informs our winding design process. That means that our winding must create the same number of pole pairs as our magnetizing field has. Now if we take this result and we finish evaluating our integral, we get the following. And so we have this expression for torque that is equal to 2 pi r squared times the axial length. And remember that r is our rotor diameter, which means that this whole expression right here is actually an expression for the volume of our rotor. And then over here, you see that we have a function that goes by the sign of alpha w minus theta. Well, theta is the position of our rotor. It's the angular location of our rotor. So as our rotor rotates counterclockwise, theta goes from 0 to 2 pi. Alpha w is the angle that we excite our sinusoidal currents at. And so alpha w we can control. Theta is the position of our rotor, but alpha w is in the hands of our motor drive. We get to pick what alpha w is. So we are going to pick alpha w as follows. And we get this expression that the torque is equal to the volume of a rotor times b delta hat, that was the peak of our magnetizing field, times a hat, that is the peak of our linear current density, divided by 2, times the sine of phi, where phi is a phase angle. So we're picking our rotor currents to track our rotor. That's why we got this theta in up here. And with some offset, with some angle phi, different from our rotor. And so you can see that if phi is equal to 0, we create no torque. And if phi is equal to 90 degrees, we create a maximum amount of torque. So let's add a little bit more physical context for what this expression means. We've already said that theta is our rotor angle. And if you recall, alpha w is equal to the location of our equivalent circumferential current density. So let's sketch this. Let's sketch an equivalent diagram. So we've got our motor model where we've labeled our direct axis, and theta is the angle to the center of our North Pole. We can then sketch that we have an equivalent surface current density somewhere. And in this case, what we were just drawing is the basis for this expression right here. This is what we sketched in a previous video when you had this equivalent surface current density that's rotating and is at some angle alpha w. We previously sketched the same winding diagram. And alpha w is equal to theta plus phi I, which we can solve for phi I as alpha w minus theta. So therefore phi I is this angle right here. If phi I is a constant, then as our rotor rotates, our equivalent winding is rotating ahead of it by the angle phi I. And we can write down some observations about this from a motor drive's perspective. When phi I is equal to 0 degrees, the sine of 0 degrees is 0, so that means we create no torque. And if phi I is 0, that means that our current is the cosine of our rotor angle. Alpha w equals theta when phi equals 0. And that corresponds to a direct access motor current. That would mean that alpha w would be aligned with theta. And you can see in that situation, if you flow a current when alpha w is aligned with theta, you're going to either enhance your magnetic field, that's called field strengthening, or if you flow a negative current, you're going to weaken your magnetic field, and that's called field weakening. And you'll talk about that in your drives classes. We'll hint at it a little bit in this class, but this class is more focused on the design of the machine. So we can say that this direct access current, when alpha w is aligned with theta, is responsible for changing our magnetizing field. On the other hand, when phi I is equal to 90 degrees, we're getting the maximum amount of torque. All of our current is creating torque. And we call that quadrature axis current, or q-axis current. And we can sketch the quadrature axis on here. The direct axis of a motor is the center of its north pole, and the quadrature axis is 90 degrees ahead of that. It's the space in between the poles. So when alpha w is aligned with the quadrature axis, that is, it leads the rotor's north pole by 90 degrees, that is when you're creating the maximum amount of torque in the counterclockwise direction. If it lags the north pole by 90 degrees, if the winding is centered about here, then it's creating torque in the clockwise direction. And all of this represents a fundamental shift from our thinking about a current as being at a certain frequency to thinking about a current as depending on the rotor angle. So our phase currents become this expression. And if theta is equal to omega t, it becomes the familiar expression that we talked about in our previous video. Okay, let's go back to this equation. This is a pretty remarkable result when you think about it. We've gone from talking about different currents and current densities and linear current densities, which produced fields in the gap of our machine that in fact depended on the number of poles of the machine. So you see that we've got an n down here, and remember we've proven that this n is going to equal p. So we went from this case where we had these expressions for a surface current density that had kind of a complicated set of terms, to being able to distill it down to just a few simple terms: the volume of our rotor, the peak of our magnetizing field, and the peak of our equivalent linear current density. It did not matter how many poles we had. It was strictly this expression. And so it starts to become clear that these are fundamental quantities of our electric machine. And there's a traditional way of expressing this equation, which I'm going to show you now, where we single this portion out here and recognize that it's actually the average of our shear in our air gap. So let me write this out. And I'll let you prove this for yourself, that if you go back to this integral up here and you find the average of the shear stress, it ends up being this quantity right here. And B delta is called the magnetic loading of an electric machine. That is the fundamental harmonic component of your air gap flux density under no load conditions is a key property of a machine, and that's called the magnetic loading. A hat, the peak, the amplitude of your linear current density, is also a fundamental property of an electric machine, and that's called the electric loading. And then phi I is a runtime decision. Your drive selects what phi I is going to be, so that's not a property of the machine. But the key properties of the machine here are the magnetic loading, the electric loading, the achievable shear stress in your air gap, and then the volume of your rotor. And when you design a motor, you can be told that you need to make some newton meters of force, maybe 100 newton meters of force, and then you get to choose. How do you want to create that? Do you want to create that by having a large rotor with a small shear stress? Or do you want to have a very compact rotor and a large shear stress? And when you make that decision, then you can go and narrow down. So now you know your rotor volume. You can determine what your rotor diameter should be versus what your length should be. That's called the aspect ratio of the motor, what its diameter to length ratio is. And there's decisions that will factor in for that. Consequences can be things like rotor dynamics, how flexible your rotor is. If it's a long, thin rotor, it's very flexible. If it's a very thick and short rotor, it's going to have what's called good rotor dynamics, but maybe it doesn't fit the form factor you're trying to design for. And if you determine what your average shear stress should be, then you have choices you can make in terms of how you accomplish that between your magnetic loading and your electric loading. And again, there's physics here at play that prevent you from choosing any arbitrary value. You can't, for example, have a 10 Tesla field in your air gap. Your steel would be totally saturated and you might as well not have any steel in it. Or you couldn't have a mega amp per meter electric loading because you'd overheat everything. It would just melt down. So when you go to design a motor, a good designer will have accumulated a set of tables of reasonable ranges that can be achievable for all these quantities. And your textbook actually provides this information for you. So in your textbook, I'm now going to summarize a table in your textbook, and this is table 6.4. I want you all to take a look at this. It gives you ranges of achievable peak linear current density, or actually, let me say that differently. It gives you ranges of achievable RMS linear current density based on whether you're operating in air or you're liquid cooled. And it gives you achievable values of your magnetic loading, and it calls this B delta 1 hat. So that is the peak of the fundamental component of your air gap field. We called it B delta in this exercise because I was not keeping track of harmonics. I was assuming everything was at the fundamental. And with conventional materials, it's reasonable to get between 0.7 and 1.05 Tesla. At the lower end of this is induction motors or high-speed motors. And at the high end of this are synchronous machines. And then you can talk about achievable values of your average tangential stress, your average shear stress, and the book does not put brackets around that. And the last comment to make on this is that the book defines a quantity called zeta. And zeta is equal to, in our nomenclature here in this lecture, it's equal to phi plus pi by 2. So we can go back up to our diagram up here, and we can note that zeta is going to be this all the way here. It's the location of your conductor coming out of the page at you. So we referenced our current density to the location where you have no current on the inner board of your stator, but the book is referencing it to the location where you have a peak current. And so if you just make this simple transformation, phi plus pi by 2, then the book will define for you typical values of the cosine of zeta. So cosine of zeta is typically 0.8 for induction machines, and it's typically 1 for synchronous motors. And the reason that it's 0.8 for induction machines is that you need to use some of your current to magnetize your machine. A portion of your stator current is actually going to magnetize the rotor and induce currents in the rotor bars. So that's to say, you are dependent on having a portion of d-axis current in order to keep the machine magnetized for an induction motor. So, in summary, in this video, we have taken the results of our previous series of videos on the equivalent surface current density and the fields produced by polyphase windings, and we've used this to derive the fundamental sizing law of electric machines. That sizing law is in this red box here. And we've talked about how you could use this sizing law to dimension your machine. This helps you invert the problem. It helps you go from being able to analyze a machine to being able to design a machine. So you can receive a design specification for a certain amount of torque, and you can go to the sizing law and start to make decisions about how you will achieve that torque between the volume of your machine and your average shear stress. And then we've given you a table of values that has been accumulated from years of practical design experience so that you can actually start to make these decisions yourself. You can see, well, if I'm going to achieve a certain shear stress, this is how much I can get. This is how much magnetic loading I can get. Or if I want to avoid using liquid cooling, this is about as good of a job as I can do with electric loading. Whereas if I'm willing to use liquid cooling, now all of a sudden I can have much higher electric loading, and therefore I can make my torque using a smaller rotor because sigma F is larger. And the point of all of this was to give you a physical basis for where this comes from.